Okay, so well, there's one thing that one small thing that I wanted to tell you. I have uploaded exactly the same slide that you're not that now you're looking at in the PRMS. So because I was able to see some of you struggling to taking note while watching the slide, but well, my slide was like moving so fast. And I was not too happy about that. So that is the reason that why I uploaded the slide on the PRMS. And sorry about that. Okay. So last time, we did the spectral theorem. The spectral theorem, well, is this is not mathematical statement, but well, this is my own opinion. But in my opinion, that one of the greatest theorem that you can ever find in the linear algebra course. So every Hermitian matrix is always diagonalism. So why is it so great? Because well, you know, if two eigenvectors that belongs to different eigenvalues, then those two eigenvectors are automatically orthogonal to each other. And also for any single eigenspace, you can find two different eigenbases inside of the eigenspace. But well, a priori, those two eigenbases in the same eigenspace may not be orthogonal to each other, right? But you can still fix that because, well, maybe you want to apply the Gram-Schmidt process to that eigenspace. Then the basis that you found from after the Gram-Schmidt process, then those bases should be still the eigenbases, so eigenvectors, and they're going to be orthonormal to each other. Therefore, by doing so, in theory, you can find a linearly independent, full set of linearly independent vectors, eigenvectors, and they are mutually orthonormal to each other. So isn't that great? So because of the reason, so I can say we can find the orthonormal eigenbasis. So therefore, so matrix A is similar to some diagonal matrix lambda. Hey, by the way, do you remember the definition of the orthogonal matrix? So what was the orthogonal matrix? Orthogonal matrix was a square matrix whose columns are mutually orthonormal to each other, right? And the mathematical equivalent definition of the orthogonal matrix is a square matrix whose inverse is its own transpose, right? But you have to remember we are now working on not real matrices but complex matrices. And in the world of complex matrices, the notion of transpose should be replaced by the Hermitian. So if you can find a orthonormal eigenbasis, then the columns of this matrix U should consist of these orthonormal eigenbases. And every column of this matrix U must be mutually orthonormal to each other. That means their inner product must be either 0 or 1. But you have to remember, in complex vectors or complex matrices, taking inner product is not just V transpose times V. It's always V Hermitian times V, right? So because of that reason, since U is Hermitian, so complex matrices, therefore, this is not U transpose U equals to I, but U Hermitian of U equals to I. So this is the crucial difference between the complex matrix and the real matrix. Okay. Okay, so and the remark number 2. Even though the spectral theorem is about the complex matrix, but real numbers are always a subset of complex numbers. So, well, we can translate the spectral theorem in the world of the real matrices. So in the real matrices, So in the world of the real matrices, the Hermitian is now transpose. And being Hermitian matrix, it means the symmetric matrix, right? Therefore, every real and symmetric matrix has allows a diagonalization, right? And well, you know, even though your matrix is real square matrix, but the eigenvalue of that matrix can be complex, right? But if your matrix is symmetric, then your eigenvalue always must be real numbers. Why? Because in my previous lecture, so we have proved that every Hermitian matrix has the real eigenvalues, right? And symmetric real symmetric matrix is Hermitian matrix. Therefore, their eigenvalues must be always real. So therefore, all eigenvalues of real symmetric matrix A must be always real. And okay, and in that case, so if basis of if the eigenvalues of A are real, then their eigenvectors are always the real vectors. Therefore, if matrix Q, if columns of Q are the orthonormal eigenbases of A, then its own inverse. This is the inverse of this guy is Q transpose, right? Because Q is an orthogonal matrix. So in that case, A is similar to some diagonal matrix lambda, and the diagonal entries of these guys are all real, and A and lambda, they are similar to each other by this real orthogonal matrix. Okay. So this is the real version of the spectral theorem. Isn't it great? Yeah. Okay. So the next definition is I will need to develop some word for if the matrix whose Hermitian is the inverse of itself. So if A is some complex n by n matrix such that its inverse is the same as the Hermitian of itself, then the matrix A is called a unitary matrix. So unitary matrix is a complex version of the orthogonal matrix. Okay. All right. And again, well, from time to time, I consider a n by n matrix to be a linear transformation from some n-dimensional vector space to another n-dimensional vector space. So multiplying some vector to the right of some another matrix can be considered as a function value of the vector x under the linear transformation U. And so in this sense, a unitary matrix U always preserves the length of the vector. So in other words, if you compare the length of the resulting vector and the length of the original vector, they are always the same thing. They are always the same. The proof is very elementary. Because, if you try to compute the length of this UX, but this, Hermitian, because this is Hermitian, therefore the order has to be reversed. So XH times UH, but these two guys are their inverses to each other, so they cancel. So I have X Hermitian times X. So the proof is very easy. And there's a direct consequence of this proposition. Every eigenvalue of unitary matrix must always have the length equals to 1. If your matrix is unitary matrix, then in that case your eigenvalue can be some complex number, right? Because but even though your eigenvalue is some complex number, the magnitude of that eigenvalue always has to be 1. Again, the proof is very elementary. Just look at this proof. If Ux is lambda times x, then you just compare the length of x and the eigenvector x and length of U, but this is just simply lambda times x, but some scalar multiple times another vector. The length of this guy is the magnitude of this number times this, the length of this vector, length of the eigenvector. Therefore, the lambda must be, the length of the lambda or the magnitude of lambda has to be 1. Okay. Yeah. So that is, well, that's about the theory. Now, why don't we just work on some concrete example? We diagonalize the following Hermitian matrix. Well, I believe some of you are not very familiar with working on some complex valued matrix and vectors. So if you think that is your case, then I strongly recommend you to spend enough time and effort working on some examples on the complex matrices. Yeah. Well, we all know that the working on the complex matrix and real matrix, they are not that different. But if you have not, it's like the working out in the gym. So well, you cannot gain your strength just by looking at the gym. So you actually need to go to the gym and work out. So same thing is true in the world of mathematics. So if you think you need to work on some complex vectors and complex matrices, then just do it with pen and paper. If you spend enough time and effort. This is a Hermitian matrix. Well, this is Hermitian, right? Because it is invariant under the conjugate transpose. And I am trying to compute its characteristic polynomial. Well, so minus 1 minus lambda times 0 minus lambda minus this guy times that. So they are complex conjugate to each other. So it turns out I have, so this is the characteristic polynomial of the matrix. And according to theory, every Hermitian matrix has the real eigenvalues. Therefore, and as we expected, so this guy can be factored into 2 linear polynomials of the real coefficient. Okay, so it has 2 real, it has real eigenvalues. The first one is 1, and the other one is -2. If lambda is 1, then I found this is my eigenvector. Okay. Now, but I want to normalize this. Well, so actually you don't need to normalize that, but well, so I want my result to be something that is written in the spectral theorem. And in order to make such a unitary matrix U, then I will definitely have to normalize this matrix. Normalize this vector. How you normalize this? You just divide this vector. You just divide this vector by its own length. And how you find the length of this guy? You compute the magnitude square of this one and plus magnitude of square of that guy, and you add them together and you take a square root. And that is going to be the length, right? So it turns out, well, so what is this? So I have divided this vector by its own length and division. So this is the result. And the same thing is true for the second eigenvector. It's the second eigenvalue, lambda 2. Then you get the same, you get the eigenvector like this. And again, you normalize, you divide this guy by its own length. And you have this. And I also want you to take a complex inner product of these 2 vectors. So how you take a complex inner product of these 2? So you take a conjugate transpose of this guy, and you multiply that row vector to this column vector. And just please make sure that the answer equals to 0. So in this case, I just put this column to the first column here, and I use this guy as my second column of this matrix. And this and inverse of this, so the same guy, but taken Hermitian. And the matrix in the middle is diagonal matrix, since this is the first eigenvector. So this first column is the eigenvector of the eigenvalue 1. So the 1 appears here. And the second column is an eigenvector of eigenvalue -2. So the second diagonal entry is -2. Has to be -2 over there. And also, the linear algebra is not about theory. So linear algebra is always about the actual practical computation. So I also strongly recommend you to compute this, take a matrix product of these three matrices, and just make sure that the result is the same as the original matrix. Okay. All right. Finally, so there is a small definition over here. A matrix is called the skew Hermitian if the Hermitian of the matrix is the same as the minus of itself. Do you remember the definition of the skew symmetric matrix? In the world of the real matrix, if any real matrix is the same as is minus of its transpose, then we said the matrix is skew symmetric matrix. And skew Hermitian matrix is a complex version of the skew symmetric matrix. Okay, good. Right. And the similarity transformation. You know what I mean by two matrices are similar. So two matrices are similar if there is some non-singular matrix M such that A is M times B times M inverse. So being two matrices similar to each other means that those two matrices are representing the same linear transformations, but the only difference is the choice of the basis. Okay. And let me turn to the next theorem. This is probably the biggest theorem in this section, which is about the Shor's lemma. Okay, so I will give you some time to read the theorem. So it says something like this: for every A is some complex matrix. Every complex square matrix A, there is an unitary matrix U of the same size U, such that T is U inverse times A times U. So A is similar to some matrix T, and what is this T? T is an upper triangular matrix. So the theorem says something like this. So every square matrix is similar to some upper triangular matrix. Okay, that is not very surprising fact because we try the elementary row operations to the matrix, and so we always made some matrix into some upper triangular matrix. So that is not very striking fact, but the most interesting part of this theorem is you can always choose your matrix M to be unitary matrix. So every matrix is not only similar to some triangular matrix, but you can make it similar to the triangular matrix by using some unitary matrix. So, I say, so in this case, sometimes I say the matrix A is unitarily similar to the matrix T. So in other words, every matrix is unitarily similar to some triangular matrix. Yeah, now this is getting more interesting. All right. Okay, so how do you prove this? Using the mathematical induction. Well, to be honest, there's something that I really want to tell about the mathematical induction. Even though mathematical induction is one of the most powerful tools that you can ever find in the mathematics, right? But mathematical induction sometimes fails to give us any intuition or any geometric viewpoint towards the theory. In this case, yeah, this is true. Well, the proof is very elegant and it has no flaw at all. But however, you may not be able to get any intuition out of this. But okay, let me just try to follow the proof given by the Professor Strang. So we try the induction on N. hey, what is n? N means the size of the matrix A. Well, if n equals to 1, so if A is just 1 by 1 matrix, like this, then A is automatically unitarily similar to some upper triangular matrix, right? So because a 1 by 1 matrix whose only entry equals to 1 is going to be clearly unitary matrix. So there's not much. So there's nothing to prove here. So the base case is done. Now suppose the theorem is true for some integer n. Now I want to prove the theorem for the case of n plus 1. So just choose any matrix from the n plus 1 by n plus 1 matrices. And you have to remember that every matrix, every square matrix always has at least one eigenvalue, and that eigenvalue has at least one eigenvector, right? So here in this n plus 1 by n plus 1 matrix A, it also has one eigenvector and one eigenvalue. So we say A times U equals to lambda times U. And without losing too much generality, so okay, you're always free to choose the length of your own eigenvector. So for simplicity, so I will choose my length of my eigenvector U to be 1. So U is a unit vector. Okay, all right. And next, we apply the Gram-Schmidt algorithm. So applying the Gram-Schmidt algorithm, you can always find an orthonormal basis such that whose first vector is precisely this eigenvector U. And you're free to choose all the other eigenvectors, so all the other bases. So these guys, they don't have to be the eigenvectors of A, they are just some random orthonormal basis of the entire vector space Cn plus 1. Okay. Then I am introducing you a sorry. Okay, good. So I am introducing you some n plus 1 by n plus 1 matrix U, whose columns are precisely these orthonormal unit vectors, orthonormal vectors. And so therefore, by its own construction, so this guy is going to be a unitary matrix. Okay. Okay. What now? And I multiply the matrix A by this unitary matrix U, 1. So this U1 is, I am replacing this U1 by these columns, this matrix. And the columns of the resulting matrix are, so A times U1, sorry, A times U, A times U1, A times UN, right? They must be the columns of the resulting matrix. And what I want to do is, I want to write down each of these columns as a linear combination of these basis vectors. Yeah, that must be doable, right? So what is the linear combination of this vector? Well, writing down this guy as a linear combination of this, but this is very easy because our definition, U was assumed to be the eigenvector of A. So A times U is just lambda times U, right? So this guy is just lambda times U plus 0 times U1, 0 times U2, 0 times UN, right? So because of that reason, the first column over here is just lambda and 0, 0, 0, 0, bunch of zeros. What about the other guys from AU1 to AUN? Yeah, clearly you can express these vectors, these column vectors as a linear combinations of these guys, but I don't care about them too much. They could be just some random numbers, random coefficient. So I'll just put a bunch of stars over here. Okay. So, and I'm just cherry picking this part of this matrix, and this is a n by n matrix. So these parts and this n by n matrix, I'm gonna declare it to be A prime. Okay, so A prime is an n by n matrix. Now it's time to use my induction hypothesis. So, well, we have assumed that the Schur's lemma is working on n by n matrices. So n by n matrix A prime can be written, so is always unitarily similar to some triangular matrix T. So that is A prime is a unitary matrix U2. This is, they are all n by n. U2 times upper triangular matrix T times U2 inverse. Okay. All right. So now I will play a little trick to this matrix. What if I multiply this matrix to the left by that matrix and to the right by this matrix? So this is this U, this matrix U is this unitary matrix. Then if I multiply this matrix by this and that, and now they are n plus 1 by n plus 1 matrices, and these are block matrices. And I am pretty sure that this matrix is again a unitary matrix. Why? Because the columns of these guys are columns of U2. They are all orthonormal vectors, and clearly, therefore, columns of these matrices they are always also orthonormal to each other, right? So this is a unitary matrix, and what do you think is the inverse of this matrix? The inverse of this matrix is precisely this one, right? Okay. So this guy is unitary matrix, and this guy is the inverse of this one. Okay. So, and if you multiply these three matrices, then the resulting matrix is going to be this. Oh, wait, why? Because, yeah, so A prime was U squared, U2 times T times U2 inverse. Therefore, T is U2 inverse times A prime times U. So if you multiply these box matrices, then you're going to get T, right? So this is the result of this computation, this matrix multiplication. Hold on. And this last mirror, this final matrix on the right is an upper triangular matrix, right? Because T was assumed to be upper triangular. Therefore, this matrix is still upper triangular. Okay? All right. Now I'm going to change a little bit. The matrix in the middle was what? Well, this guy is the same as this one. But solving this equation for this matrix, and this is my matrix U. This is U1, right? So this matrix is U1 inverse times A times U1, right? So replacing this matrix in the middle by U1 inverse times A times U, and right. And also, I also need to make sure that the product of two unitary matrix is again another unitary matrix, right? And this is a unitary matrix. This is a unitary matrix, and this guy U1, this is another unitary matrix, right? So unitary times unitary. So this matrix U1 times this unitary matrix, which I will call just U, simply U. And this matrix inverse times U1 inverse is going to be then U inverse, right? So A times unitary matrix U times U inverse is what? This upper triangular matrix. So therefore, my n plus 1 by n plus 1 matrix A is unitarily similar to some upper triangular matrix. So this is the end of the story. Okay. All right. Great. The next definition is a matrix is normal. So normal matrix. We say a matrix, so square matrix is normal if the matrix is commuting to its own Hermitian. So A times AH times A Hermitian times A is A times A Hermitian. If those two matrices commute, then we say the matrix is normal matrix. Okay, why are we interested in the normal matrices? Because if you look at the next theorem, and it says A square matrix is diagonalizable and has orthonormal bases if and only if A is normal. Aha. So in other words, a matrix A is unitarily similar to some diagonal matrix if and only if A is a normal matrix. Okay. Okay. Before I prove this, okay, suppose that we are just believing in the theorem. Then spectral theorem is not a striking theorem anymore. Why? Because spectral theorem says every Hermitian matrix is unitarily or similar to some diagonal matrix, right? That is the main part of the spectral theorem. But, well, Hermitian matrix is automatically normal, right? Because A Hermitian, so a matrix A being Hermitian means the matrix is invariant under the Hermitian. Therefore, that means the Hermitian matrix automatically normal matrix, right? Aha. And the theorem says a unitarily similar to some diagonal matrix is mathematically equivalent to A is a normal matrix. Okay. All right. So what is the proof of this? So this is an if and only if statement. So therefore, you have to prove the two-sided implications. And I guess this direction is easier than the other one. So let me prove this side first. Suppose that A is a diagonal. A allows diagonalization and has an orthonormal eigenbasis. So in other words, A can be written as some unitary matrix U times diagonal matrix lambda times U Hermitian. All right. So all I need to do is I must show that A is normal matrix. In other words, I have to show that A times AH is AH times A. Sorry. Okay, so here I am replacing every appearance of A by U times A is lambda times U of H. So this is this. And since there is a Hermitian over here, so, well, getting rid of this parent is this. Yeah, you have to reverse the order of these matrices. So U Hermitian, which is just U, and lambda Hermitian here and U Hermitian over there. But U Hermitian times U, they are inverses to each other, so they just cancel. So U times lambda Hermitian times U Hermitian. Okay, but lambda is a diagonal matrix. Therefore, lambda and lambda Hermitian, they can commute each other. So this is lambda Hermitian times lambda times U Hermitian. And after then, I'm just putting one addition. So between lambda Hermitian and lambda, between these two matrices, I am plugging in, I'm inserting additional UH times U because this is an identity matrix. And you can easily see that this is the A Hermitian times A. So now I know A is a normal matrix. Okay. Okay. Not a big deal. What about the other side? Yeah, this is the hard. This is the hard part. And to prove to prove this direction of the implication, I must make use of the Shor's lemma. According to Shor's lemma, every square matrix is unitarily similar to some upper triangular matrix T. Just like this. Okay. And so we have to assume that A is a normal matrix. So A is a normal matrix. So A times AH is AH times A. In other words, well, every A has now been replaced by UT and UH. So just like this. Okay, good. And these guys, so they are inverses to each other, so we can easily cancel them out. Likewise, we can cancel these U's and these UH's to both sides from the both sides of these equations. So what I have is just TTH is TH times T. Okay. So A being normal implies that T times TH is TH times T. What I want to do from now on is I want to prove that T is a diagonal matrix. T is a diagonal matrix. Well, if I can prove that T is a diagonal matrix, then this T is a diagonal matrix. Therefore, A is unitarily similar to some diagonal matrix, right? Therefore, my claim has been proved. Okay. So how do I prove that T is a diagonal matrix? Yeah. To make a visually appealing the proof, so this is my matrix T, which is an upper triangular matrix, and we are now imposing this upper triangular matrix T is satisfying the relation. So I have this. This is the equation on the right. So the equation on the left is TH times T. Right? This is the conjugate transpose of the original matrix T. This is T times TH. Okay. And we know that this matrix is the same as the other matrix. And in order to matrices to be the same matrix, then their entries must be all the same thing. So every entry must be the same. So therefore, I just want to focus on the 1-1 entry of the both sides of equations. So what is the 1-1 entry of the matrix on the left? So 1-1 to get the 1-1 entry, so I will need to multiply this row by this column, right? But there is only one entry here. So T11 conjugate and T11. So the 1-1 entry of THT is just the magnitude of the T11 squared. Okay. On the other hand, the 1-1 entry of the matrix on the right is obtained by multiplying this row by this column. And so this guy times this, and this guy times that, this guy times that. And you take summation of them. And as you can see from here, they are complex conjugate to each other. Therefore, the 1-1 entry of TTH is going to be the summation of the magnitude square of each of these guys. Okay. Okay. This is not okay. So comparing these two. So I can so these number and that number, they are the two same numbers. So I can get rid of them. So I just ended up with this guy square plus this guy square times this guy square equals to 0. Okay. But you have to remember, so even though these numbers are complex numbers, but their magnitude square is always going to be some non-negative real numbers, right? So this is the summation of some non-negative real numbers, and this guy equals to 0. Therefore, the only possibility is each of these terms should be 0, right? And there is only one complex number whose magnitude equals to 0. What is that? The 0. This is the 0. So this implies that this guy square equals to 0 for all in the indices, implies that these guys should be 0 for all indices. Right? So what? Since these numbers are all 0 from I2 to n, so I can simply get rid of these entries from our consideration. Right? And you can do exactly the same thing for 2 entry and 3 entry, up to n entry. Then by doing so, you can easily convince yourself that these guys should be 0, and these guys are 0, and these guys are 0. All the entries above the diagonal should be 0. So by doing so, you can prove that T is a diagonal matrix. Therefore, our claim has been proved. Okay. All right. Now this is time to explain more on the Jordan form of the matrix. Well, I already explained that every matrix is similar to some Jordan form. So that is, you can always find some non-singular matrix M such that A is M times J times M inverse. Here, J is the Jordan form of the matrix A. Jordan form of the matrix A. And the column vectors of this matrix M are called Jordan bases. Well, even though we have discussed how to find the Jordan form of any given square matrix, but we have never said anything about the Jordan bases. And today, I will try my best to explain how to find the Jordan matrix, the Jordan basis, and the matrix M. Provided that, so assuming that you can find the Jordan form of the matrix A. All right, this is an warming. Okay, let me consider this exercise to be our warming up exercises. I have 3 2x2 matrices. They seem to be completely different to each other, right? But I claim they are all similar to each other. Why? This is not very easy to see from the beginning, but okay. But I will justify my claim like this. First, you try to compute the eigenvalues of these 3 matrices. So to find eigenvalues, then you are supposed to compute the characteristic polynomials of these matrices. Oh, and it turns out to be their characteristic polynomials are all the same thing. They are all identical polynomials. So this gives us so it passes the first test. So their characteristic polynomials are all the same thing. So since we have found the characteristic polynomials, so we now know the eigenvalues, and these 3 matrices have just one eigenvalue, which is 1, and their algebraic multiplicities are all 2, right? Algebraic multiplicity of this guy 1 is 2, and 2. So their algebraic multiplicities are all the same. And what remains to show is, so we have to find their algebraic, geometric multiplicities. And well, this is a complicated computation. So maybe you can try it by yourself. So if you try to find the eigenvectors of these eigenvalues, then you can find only one eigenvectors for these eigenvalues. So this implies their geometric, so their dimensions of eigenspaces are all ones. Therefore, their geometric multiplicities are all ones. Right? So, okay, these three matrices, they are sharing these key properties. They have the same eigenvalues, and their algebraic and geometric multiplicities are all agreed. Therefore, what do you think is the possible Jordan form of these matrices? The Jordan form of these matrices are all the same thing. They are all similar to this Jordan form. Okay? Because in 2x2 matrices, there can be only one Jordan form of eigenvalue 1 whose algebraic multiplicity is 2 and geometric multiplicity is 1. This is only one possible Jordan form. That is fine. So since these three guys, they are all similar to this matrix, this Jordan form, therefore, they are all similar to each other. Okay, so in other words, even though those three matrices are seemingly all different, but they are just representing one single linear transformation. Only different choices of bases. Okay. All right. Good. Now, suppose that a matrix A is similar to a Jordan form consisting of single Jordan block of size K. What if not? So, well, maybe you might ask. So maybe my matrix A is similar to some Jordan form that has multiple Jordan blocks. But so if you understand how to find the Jordan basis of one single Jordan block, then you can apply the same trick to another Jordan block, and you can find all the Jordan bases. So for simplicity, so let me say A is similar to one single Jordan block. So in this case, M inverse times M A times M, so equals to the Jordan block J, and this is the K by K Jordan block. So I have K diagonal entries and K minus ones over here, and I am multiplying the both sides by the M. So now, so that is A times M is M times J, and this is M and this is J. And I'm going to say the columns of M is consisting of these columns. So I would say this is my M. So A times M is here, and M times J is this. And so I'm going to analyze this resulting matrix column by columns. So, well, the first column of this resulting matrix is lambda times V1 plus 0 times V2 plus 0 times V3, 0 times Vk. So therefore, the first column of the resulting matrix is lambda times V1. The second column is 1 times V1 and lambda times V2 times 0 times V3, So therefore, lambda times V2 plus V1, this is my second column. And for the third column, the 0 times V1, 1 times V2, And well, there's an invisible lambda over here, lambda times B3. And so this is going to be your third column. And likewise, this is your last column. Okay. And we know that this matrix is the same as that matrix. And let us compare the left and right column by column. So the first column of the matrix on the left is A times B1, right? So A times B1 should be the same as lambda times B1. So which is the first relation over here. And A times B2 should be the same as lambda times B2 plus B1, which is this second relation. And A times B3 should be lambda times B3 plus B2. Like this. So So all the way up to the case column. So A times BK is lambda times BK plus BK minus 1. Okay, so we now have this relation, okay, all right. So let me just move these terms to the other side of the equation. Then if I send this guy to this side, then A minus lambda times I, everything multiplied by V1 equals to 0. And descending this guy to this side, A times lambda times I, A minus lambda times I times B2 is B1. And A minus lambda I times B3 is B2, A minus lambda I times BK is BK minus 1. So I just ended up with this K such relations. Okay, so what is this? What is the meaning of this bunch of relations? I want you to focus on the first relation. What is the vector satisfying this relation? A vector satisfying this first relation is going to be the eigenvector, right? Okay, So V1 is nothing but the eigenvector of eigenvalue lambda. Hold on, but we are assuming that A is similar to a single Jordan block. A single Jordan, then how many linearly independent eigenvectors can you find from a single Jordan block? Only one, because every single Jordan block is corresponding to geometric multiplicity 1. So if your matrix is similar to a single Jordan block, then you can always find only one single eigenvector, linearly independent eigenvector. So this guy is that eigenvector. And this eigenvector is something that you can easily find by some tedious computation. All right. Suppose that, okay, let us suppose that you were able to find the vector V1. And once you found vector V1, now you solve this relation for vector V2. Okay. And if you can find vector V2, then you plug in this vector V2 into this third relation, and you solve this relation for V3, right? And proceeding like this, then you can find the vector Vk all the way to the vector Vk. Okay. Once you found all these vectors from V1 to Vk, so I say this is sequence of vectors from V1 to Vk, and these vectors, this set of vectors is going to be precisely the Jordan basis that you're looking for. This is how you find the Jordan basis. Okay. Okay. So this is the summary. This is summary of what I have spelled out so far. So for each basis vector, so therefore, so for this given eigenspace E of lambda, then you can find the basis vectors of this eigenspace, and for each basis vector V, then we are letting this guy to be our V1, and we try to find the sequence of vectors from V1 to Vk. Then if you can find the sequence of vector V1 to Vk, then that is going to be the Jordan basis of your Jordan basis of Jordan block of size K. Okay. Now this is getting somehow confusing. All right. So that is which is very natural. I've been expecting that. So why don't we work on some concrete example? All right. Yeah. This is a 2x2 matrix. And let us try to determine its Jordan form. And plus, we try to find its Jordan basis of this matrix. The first thing that we need to do is we are supposed to find the characteristic polynomial of this matrix. This is very routine computation, so I don't want to waste too much time on that. So its characteristic polynomial is lambda minus 1 to the 4th. So I have only one eigenvalue, 1, and whose algebraic multiplicity is 4. And again, by some tedious computation that I don't want to repeat, the eigenspace of this eigenvalue has been spanned by these two linearly independent vectors. So, and these vectors are clearly going to be the eigenvectors of this eigenvalue, right? All right. So the dimension of this guy, the eigenspace is 2. So its algebraic multiplicity is 4, and the geometric multiplicity is 2. So, well, if you're remembering my lecture correctly, then you know there can be only 2 possible Jordan form of this guy. So then either Jordan form of A must be either this guy or that. Okay. Which one is right? Well, okay. So frankly speaking, so this is the Jordan form of the matrix A. How do I know that fast? Because this is precisely the same exercise that we did in the previous lecture. All right. So okay, but let us pretend not knowing the Jordan form of the matrix A. Okay. So forget about the Jordan form of A for now, and suppose that we are looking for the Jordan basis of the matrix A. And here in this eigenspace, I have 2 basis vectors, this guy and that guy. And I will need to find the sequence of vectors V1 to Vk for every basis vectors from this eigenspace. So I have 2 choices, this guy or that guy. And first, I am going to declare this guy to be my V1. I'm going to set this guy to be my V1, and I will try to find the sequence of vectors V1 to Vk, starting from here. Okay, so this is my V1. And this is my V1. So I am plugging in this V1 over here, and I will try to find the vector V2 satisfying the second relation. So A minus lambda I. So this lambda is just 1, you know. A minus I times V2, which is this, is V1. This is V1, right? And this vector, this column vector, V1, V2, V3, and V4, and this guy is my V2. So I am looking for V1, V2, V3, and V4 satisfying this relation. Okay, and fortunately enough, so the first law and the second law, they are identical, right? So multiplying, so expanding this, so I have these 4 equations. Okay, so V0 times V1, so there's no V1, V2, and V3, V4. Okay, and they are just 1, 0, and 0, and 0. And well, hold on. I am pretty sure that I cannot find a solution of this system. Why? Because can you realize, can you see that the left-hand side of the first and second equation are the same thing. But the right-hand side of the first equation is 1, and the other equation, the second equation is 0. So 1 can never be the same as 0, right? So which implies that there is no solution of this system. Right? That means there is no such V2. Which again, that implies if this guy is your V1, then your sequence of vectors just terminate at k equals to 1. Right? Right? So, well, okay, remember, you're supposed to find this sequence of vectors from V1 to Vk. But your sequence of vector is terminating at k equals to 1. Right? So that means this V1, this, well, you know, so every basis vectors of this eigenspace must correspond to some Jordan block, right? Because one Jordan block is corresponding to a one geometric multiplicity, right? And, well, if the sequence of this vector, sequence of vectors starting from this guy is terminating at k equals to 1 means there is a Jordan block of size k equals to 1, right? So that means you must expect there is a Jordan block of size 1, like this. So that automatically eliminates this possibility. This guy can never be your Jordan form, right? And this vector is going to be the basis for this Jordan block. Okay, good. All right, we are still in the wood. So, all right, now what about the Jordan block of the Jordan basis of the second Jordan block? Jordan block of size 3. So in order to find the Jordan block of the Jordan basis of this Jordan block, then this time around, I will need to take this guy, the second basis vector, to be my V1. So here I have chosen the second vector to be my V1. Well, this is my V1. And again, I'm doing the same thing. So this is my V1, and I am looking for the vector V to satisfy the second relation. So A minus lambda I times V2 is V1. So this is A minus lambda I. And this is my V2, and this is my V1. Okay. Again, I get this systems of equations. All right. So this is my this shows my struggle to find the solutions of this vector V1, V2, V3, and V4. So I solve this last equation for V4, then V4 is just 1 plus V3, right? And I am plugging in this V4 into the third and second equation. And well, according to third equation, V2 is just V4 plus 1. And replacing this V4 by 1 plus V3, I have this guy equals to V3 plus 2, right? So V2 is just V3 plus 2. And I am doing the same thing for the second equation. Well, in this V4, I am replacing this V4 by 1 plus V3. And so V2, and solving this for V2, so V2 here is minus V3 plus 3 times V4 minus 1. And V4, replace this V4 by 1 plus V3 over here. And solving this, I ended up with V3 plus 2. So, and these two expressions, they agree. Okay, so this is, which is very consistent. So therefore, this is my V2, which is assumed to be V1, V2, V3, and V4. And V1 is just still V1. And V2 is V3 plus 2. And V3 is V3. And V4 is V3 plus 1. And well, and for cosmetic reasons, sorry. Well, V1 is, I would just say V1 is alpha and V3 is beta. So alpha, beta plus 2, beta, beta plus 1. So this is going to be, this guy is going to be my V2. Okay. All right, great. So now I found V2. Now I want to find V3. Okay, to find V3, so now we know, now we have found V2. So we plug in V2 over here and we will solve this equation for V3. All right, so let's do this. So A minus lambda times I times V3. So this is V3 and this is A minus lambda I. And here on the right-hand side, this is my V2. This is V2. Now it's here. And again, so I am solving this. So I have 4 equations. And well, and you can easily say that alpha and this number and then that number, they must be the same number, right? Because, well, they have to be the same number, right? So alpha is the beta plus 2, which is good. Now I'm doing the same trick. I'm playing the same game. Well, I solved for the last equation for V4. And once I solve this last equation for V4, I am replacing this V4 and that V4 by V3 plus beta plus 1. And just bunch of computations. So these two results, they agree. The V3 plus 2 times beta plus 1. And plugging into here, also I get the same conclusion, same result. V2 is V3 plus 2 times beta plus 1. So this is my V3. So which is V1, V2, V3, and V4. And V1 is still V1. V2 is V3 plus 2 beta plus 1. And V3 is V3. And V4 is this. Wait. Yeah, V4. This is V4, right? So this is my V4. V4 is now here. And again, I named, so I say V1 is now gamma, and V3 is delta. And so gamma, delta plus 2 times beta plus 1. So delta plus beta plus 1. So this is my V3. So I already found all the way to, my sequence of vector is now all the way up to V3. And if you're understanding my theory correctly, then since now we all agree that this guy can never be your Jordan form of the matrix A. So, and since we already know there is Jordan form of Jordan block of size 1, so there must be Jordan block of size 3. And we already found the V1, V2, and V3. So we already found the Jordan basis of the second Jordan block of size 3. So we actually can terminate our computation right here, right at this point. Okay. So because we already found V3. But for educational purpose, so let me just pretend I just try to find the V vector V4. Then, so A minus lambda I times V4, which is this, is now V3. Then, so I get this equation and I play the same game. And so this is V4. I am plugging in this V4 over here and there. And now I'm in trouble because if I plug in this V4 over here, then this third equation says that V2 is V3 plus 2 times delta plus beta plus 1. But if I plug in this guy over here in the second equation and solving this equation for V2, then I have V3 plus 2 times delta plus beta plus 2. Can you see that this difference? This is 1 and 2. So this equation doesn't allow any solution. This is an inconsistent equation, which implies there is no solution for V4. So that means your sequence of vectors must terminate at k equals 3. Okay. So, great. All right. So, okay. Yeah, that was such a long computation. So this is V1. This is V2. But so alpha is the beta plus 2. So this alpha has to be changed to beta plus 2. And this is V3. So these are my vectors, V1, V2, and V3. But I really don't like this bunch of Greek alphabets, alpha, beta, gamma, delta. So for simplicity, I'll just plug in delta. So all these guys equal to 0. Then this is V1, and V2 is 2, 2, 0, 1. And V3 is 1, 0, 1, and 0, 1. Am I right? Am I right? Yeah, I'm right. I'm good. Okay. Okay. So, okay. Now you have to be very careful, very cautious, especially about the order of these column vectors. So this first vector, V1, so is the first column of the matrix M. And the second vector is going to be the second vector, second column, and this one, V3, is the third column. Hey, what about the last column? Because I am supposed to get the 4x4 matrix for M. But what about my last column? This last column is coming from this V1, this guy. Right? Okay. So if you multiply, then if you multiply A times M is, then A times M is M times this matrix, because these three column vectors, these three columns are Jordan basis of this first Jordan block, and this last column is the Jordan basis of this last 1x1 Jordan block. So therefore, if you multiply this matrix and you invert the matrix and multiply to the A to the left and right, then you should be able to get this Jordan form as a result. Okay. Well, so, all right. So how do you like this computation? Do you like it or not? Okay. Frankly speaking, so the computation, finding the Jordan, the algorithm that finds the Jordan form and Jordan basis of any given matrix is not very mathematically stable. So in the practical computation, so if especially you're an engineer or interested in scientific computation, that they almost rarely ask you to find the Jordan form or Jordan basis, because, well, these algorithm is not mathematically stable. But however, they are somehow very important in theoretical linear algebra. So this is the reason that why I'm spending this much time and effort explaining Jordan form and Jordan basis. Sorry about that. But I don't think this is really so. I don't think asking you to find the Jordan form or Jordan basis, especially more than 3x3 matrices, is not a great idea in the final exam. So you don't need to worry about that too much. But well, in order to obtain the mathematical completeness of this course, yeah, I feel like I need to introduce this. And okay, now what is the use of the Jordan basis? Because now we know how to find the Jordan form and Jordan basis, then we can now have a complete theory on the matrix exponentials and matrix powers. Well, do you remember that? Previously when you try to find the matrix exponentials, we always worked on the matrix that allows diagonalization, right? But what if your matrix does not allow any diagonalization? Then in that case, you cannot take the arbitrary power of your matrix. So you may not be able to get the matrix exponential. But since now we know every matrix allows the Jordan form, and if we understand how to take arbitrary power of any Jordan form, then that will enable us to find the matrix exponential of possibly non-diagonalizable matrices. So now this is getting more interesting. Maybe, at least to me. Okay, so this is end of today's story, and see you next time. Thank you for your patience.